right. Today we're doing the synthesis lab. When we do a synthesis lab, do we have to be super precise in our measurements, mass, etc.? Not so precise. We just have to know what the limiting reagent is and the excess reagent. Usually we have some buffer, we have plenty of excess reagent that we don't worry about it too much. And so the first part, and this lab, and so when we do the measurement, we aren't going to use the high precision, high accuracy, analytical balance. We're just going to use the centigram balance. The centigram balance is measures to the nearest hundredth of a gram. And so the centigram balances they have on the countertops in the back here, so we aren't going to use the balance room. We're in Chem 1A. In fact, we're going to move some of the balances into the hood because we're going to weigh some of the items in the hood rather than out here. Now, normally the hood will impact the balance, but these balances aren't that sensitive, so the hood is not going to. We'll just do it there. All right, so one thing is you don't have to spend a lot of time. If you overshoot it, just as long as you didn't overshoot it by a terrible amount, or if you undershoot it, you're okay, just as long as you're in the ballpark region. But even if you overshoot or undershoot it, you got to make sure you record the masses that you actually used. All right, now this lab report is going to be a formal lab report. We're just going to have a couple of these, and what you do in a formal lab report is you just describe what you did, and you describe the chemistry of what happened. And so let's talk about the chemistry of what's happening in this synthesis right now. The overall reaction, we're going to form an oxalate complex of chromium-3 overall. And what is, do you know what the final product is that we're after? It's K3CrC2O4, which is the oxalate ion. It turns out we can attach 3 of these oxalate ions to a chromium. Oxalate's interesting because oxalate actually will bond in 2 places. So this is still like an octahedral. When we look at what's in the parentheses, not the parentheses, but what's in the brackets here, the structure of this is going to look like this. We got this chromium here, and the chromium is going to have an octahedral configuration of these coordinate covalent bonds, or just covalent bonds like this. And the oxalates come in here. Oxalates will have a lone pair on an oxygen here, and that lone pair can bond here. Let's draw out the rest of the oxalate structure here. Now, it's very symmetric, and so another oxygen on the other side of the oxalate ion can come in and bond there. And so what it does is it bonds in 2 places here because it has these 2 oxygens. You might think it could bond in 4 places, but just because of the orientation of this particular ion, it can't. Because if you look at the carbon here, what's the hybridization on that carbon right there? What's the hybridization on this carbon? sp2. This is an sp2 carbon, which means that this geometry around this carbon is sp2. What's the geometry? Trigonal planar. Yeah, good. Oh. It's trigonal planar. So this thing's flat, like this. So we could attach this end, we could attach this end, but these 2 oxygens are pointed in the opposite direction, so those oxygens aren't going to participate. And so this one bonds in 2 places. And so, when it bonds, they have a word for that with ligands. It's called dentate. And so a regular ligand would be called a monodentate because it only bonds with one. We call this a donor atom. The base atoms are donor atoms because they're donating a pair of electrons. And so we have two donor atoms bonding in two places for one ligand. So we call oxalate a bidentate ligand. And so it only takes 3 of these bidentate ligands to fill up an octahedral configuration of bonds like this. I'm using the dashed wedge to just show the geometry around here, but I'm not going to dash and wedge the ligands because it'll get kind of messy, maybe, or maybe it'll be clearer, but it's a lot more work. So we'll just leave the ligands kind of up to your imagination, how they project in and out. And so now we have these 3 ligands. What's the charge on this complex ion? You know, and what's the name of this complex ion? Well, you know, the chromium, we have to figure out what the charge on chromium is. And we can figure out the charge on chromium because we already know what the charge on potassium is. What is the charge on potassium? +1, it's alkali metal. And so we got 3 of these positive charges, which means that this must be a 3- complex. So this whole complex is a net charge of 3-. The way I get that is, you know, chromium is 3+, right? And each oxalate is 2-. And remember, we ignore formal charge here, so we're imagining these as being C2O4 2-, all of them. But we got this covalent bond going here. And so it's kind of weird because here, these ions are going to be covalently bonded to the chromium. Now, what about the potassiums? Are the potassiums covalently bonded? No, the potassiums are ionically bonded. And so the potassiums just serve as counterions. And so what we'd have is a lattice structure. And so we put a potassium ion here in the lattice, a potassium ion here, a potassium ion here, and then we just alternate, you know, potassium ion and then another one of these. These are called, what are these called? The ion, the anion here. It's the anion called. Yeah, good. Trioxylatochromate 3 ion. So we have the trioxylatochromate 3 potassium, trioxylatochromate 3 potassium, and we build up an ionic lattice. Is it soluble or insoluble, this lattice? You know, if I have this crystal of, if I'm going to have a crystal of this, you know, I got this, and then another potassium, you know, so I form a 3-dimensional lattice, like, I don't know, like, kind of like sodium chloride or something like that, although the lattice structure is going to be different. What do you, should this salt dissolve in water, or should it be insoluble in water, this salt? It should be soluble. Why? Why did you come up with that? Yeah, group 1 salts are soluble. So this should be soluble in water. So if I dissolve this in water, what happens is the ions break apart from each other. But will the oxalate ions break apart from the chromium in water? No, it doesn't. What happens is if I dissolve this in water, this whole thing is going to stay intact. These are covalently bonded here. And so those aren't going to break when we dissolve it in water. And so the potassium ions will break off. The trioxalato, called trioxalato because we have 3 oxalates, and we change it. If it's an oxalate, we call it oxalato, and then it's chromium, but it's an anion complex, so we call it chromate. And then the Roman numeral 3 comes from this positive 3, not the negative 3, the positive 3. Because it just tells us the charge on the metal. And so this thing is called, actually, you know, when I have this as a solid, you know, some solids like this will have void spaces. Do you guys remember void spaces in crystalline lattices? What types of voids did you learn about in typical lattice, like a face-center cubic lattice? Face-center cubic lattice is the primary void spaces, and the void spaces are the spaces in between the ions and the crystal. The primary void spaces that you were concerned with were the octahedral voids and the octahedral holes. We call them holes too. The octahedral holes and the tetrahedral holes. Do you guys remember the radius ratio? The radius ratio? If you do the radius ratio, you can figure out what lattice. Like for example, if it has a radius ratio about even, you know, the radius of the cation and the radius of the anion are about the same, then it adopts the rock salt or the sodium chloride structure. Okay. If the anions are huge, and cations are small, it adopts the cesium chloride structure. You guys, or is that right? Something like that. Do you remember? Zinc blend, radius ratio. Okay. Well, anyway, some lattices can pick up water from the air. You know, because water is polar, right? Water. What do I mean by polar?
Uneven in charge.
Uneven in charge. So water has like positive side and a negative side. And so what happens is water is going to be attracted to the surface of this. And normally, you know, water becomes attracted. It's like when you have a very polar surface, water becomes attracted to it, like glass. You know, water vapor and air can stick to the surface of the glass and adhere to it. And so in chemistry, we often dry the glass, even though it looks dry. There's water stuck on the surface of it because water is polar, glass is polar, they like each other, and they get stuck together. The same thing here. If water comes to the surface, water will get stuck here. In fact, if enough water comes here, water will want to pull apart this crystal lattice. But let's say we just have water vapor and air. What happens is water vapor in air gets stuck on here, and sometimes it works its way into the lattice and gets stuck in a void space. And then what happens is we form a hydrate. A hydrate is, it depends on how many void spaces and, you know, how accessible and, you know, whatever. And so it turns out for every formula unit, because we don't have molecules here, we call it a formula unit. A formula unit would be 3 potassium ions and 1 of the complex ions. For every one of these, we can fit 3 waters into the voids. These waters get stuck in the lattice here. And 3 waters per void. Per formula unit. And so we got the water stuck here, and this whole thing is a solid, you know. And so this is just water vapor getting stuck on, or stuck inside the crystal lattice. And so this is what we're after. We're after synthesizing this, which we call potassium. Is that right? 3 waters. It's a trihydrate, we call it, or 3-hydrate. So how would we name this? Should we call it tripotassium or should we call it potassium? Tripotassium or potassium?
Potassium.
We just call it potassium because we can figure out the number of potassiums based on the anion. And the anion's called, well, somebody already mentioned, triaxalato. Now this is all one word, chromate. 3, because it's just one ion. You don't split that apart like multiple. Although, you know, hydrogen carbonate, we split up into 2 words. But anyway, potassium trioxalato trihydrate. Solid. We're going to make this stuff here. And so it should be a nice ionic lattice, which is a crystal. It should be a nice crystalline solid. All right, let's move on here. So what do we make it from? Well, we're going to make it from, like in step one. Step one, we're going to do a redox reaction. This is a redox reaction in which we're going to take this. What are we using in this lab? We're going to go take this and make that. What's this and that? We'll take dichromate and make potassium is going to be a spectator in this. So the potassium ions are pretty unreactive in both redox reactions. You know, potassium is such a weak oxidizer, it doesn't really do anything. It's also doesn't precipitate with anything. So potassium is used as spectators. We typically are going to ignore the potassiums because it's not going to do anything. This is what we're after. We need the chromium 3. We don't have chromium 3. We have chromium what? Our final product needs chromium 3, but we're starting with chromium 6. Good. So in order to go from chromium 6 to chromium 3, we need a suitable what? I need to react this with a suitable reducing agent. But I know something about this. I know something special. Tell me some properties about this ion. Well, one, don't touch this stuff, don't breathe it. You know, it's toxic stuff, but tell me some chemical properties of this. What's one thing that stands out about this ion? When I look at this ion, I automatically think something stands out. You know, oftentimes things don't stand out because they're middle of the pack or something. You know, oftentimes people will say they just remember, you know, the who's first and who's last, but everybody who's in between they forget. You know. And so something about dichromate stands out. What is it? Or is it just middle of? It could be mid-pack everything. You know, mid-pack this, mid-pack that. Chemically, what stands out about dichromate? Is it powerful at anything, or is it just weak, moderate, middle, average? Or is it powerful at something? Tell me your study habits. How do you guys study? I'll tell you how I studied. I mean, because I had to, like I told you, I had to adjust the way I studied to completely revamp how I studied. So this would have been at the tip of my tongue because I would have already seen this many times, because when we talked about dichromate, it was a while ago. And over that period of time, I would have gone through my notes multiple times and seen it. So it would have been burned into my memory. Yeah, it's not just an oxidizing agent, it's special. What's special about it? You know, it's not just an oxidizing agent, it's you're right, it is an oxidizing agent, and I want to go on in terms of that. What is it, a mid-pack oxidizer, weak oxidizer? It's a powerful oxidizer. When you have something that's a powerful, and it's a very powerful oxidizer. Because if you look in Appendix D, it's on the first page that we encountered, where gold 3 was at the bottom. You know, nitric acid was nitrate was way beyond that. Nitrate's still a powerful oxidizer. And so it's a powerful oxidizer. Well, with powerful oxidizers, how much precaution do you have to take? Is it like working with HCl? HCl is a powerful acid.
much precaution do you take with HCl? You handle it with extreme care, usually. If you got some 3 molar I got some 1 molar HCl, 3 molar HCl, I better handle that with extreme care. Or do you just splash it everywhere? Well, me, I just splash it everywhere because I don't think 3 molar HCl is not a big deal. Some people, they're sensitive to it, but 6 molar, I've spilled lots of that. The dichromate, splash some on your skin, no big deal. Well, I just leave that whole MSDS stuff, and stuff has already been wiped clean, I think, from the memory. So let me just reiterate, since today's the day of the lab. This stuff is dangerous. This stuff is a powerful oxidizer. Powerful oxidizers cause explosions. Powerful oxidizers result in the dichromate chemist handshake. You know the dichromate chemist handshake? That could be fine too, because dichromate will react explosively with. Is dichromate? Look, think about this. Does hydrogen react explosively with oxygen? Or violently? Does hydrogen react violently with oxygen? No? Have you seen hydrogen react with oxygen? Paul, have you seen hydrogen react with oxygen? The balloon, yeah. So was it explosive or was it just a mild reaction? There was a lot of explosion, right. No, it reacts explosively. Oxygen is a lot weaker of an oxidizer than dichromate. Dichromate's even more powerful. And so this stuff is dangerous. It's dangerous, so you gotta watch out what you mix it with. One day we were working with oxidizers, nitrate. It was this lab. I had it out in a different sequence. I had one student who missed the lab, so they had to come in and make up a lab. They're making up this lab. They're making up this lab, which we use ethanol. You know what ethanol is? A reducer or an oxidizer? Or no idea? If you have no idea, then what you want to do, you want to draw out the structure. Let me just do a side here. We draw out the structure of ethanol. I already did this before, I think. Draw out structures, and then tell me the oxidation states of the atoms. Here. Okay, so tell me the oxidation state on this carbon atom here. No, it's not right. Did you guys, this is it. If I do something on the board, and I find, I don't understand this either. If I do something on the board, people go, okay, I can do that, and then when it comes to the test, no, they can't do that. And then I thought, why is that? And then it's like people,